One is like this, carrying the current I in clockwise direction, and there is another loop which is carrying the current in anti-clockwise direction, and there is one point here, let me call it as a center, and therefore here somewhere the point B is lying inside it. Now I would like to find out what is the direction of a magnetic field. Now as I told you, the right thumb rule can be slightly modified for this kind of a closed loops. How it is? So if the current is going like this, then I mean either clockwise or anti-clockwise, let it be. Here the current is going in clockwise. Now I have to curl the fingers in the clockwise direction. Then my thumb will either move into or out of this plane. So here the current is going like this, therefore I have to curl my fingers in this direction. The thumb is showing into the plane of a board. Therefore at the point C, the direction of magnetic field is into. And let us come to here. Here it is like a not a pure circular loop, it is some irregular shape, let it be. So here the current is going like this. Now the thumb is stretching out, that means from out of the plane of the board. Therefore magnetic field intensity at this point due to this loop will be out of this plane of board. This is the direction of a magnetic field. This is what about the magnitude of magnetic field intensity that can be found from Biot-Savert law, and these two are the informations for the direction of a magnetic field. And let us see some applications of important applications of the Biot-Savert law. Well, so we will start here now with the applications of Biot-Savert law. Applications of Biot-Savert law. What are the applications? We will begin now by writing the formula for the magnetic field intensity due to straight conductor. So these are all we have done for irregular shaped conductor. Now I am going to tell you the formula for straight conductor. A straight conductor. Let us see. So here I am not going to give you any kind of derivations, but a simple formula and how to use them, that alone I will discuss here. And let us suppose there is a one straight conductor and there is a one point P here which is at a perpendicular distance from the straight conductor of A. Here is a point P that is lying at a perpendicular distance of A from the straight conductor, and the adherents of a conductor are subtending an angles of alpha and beta respectively. The adherents are subtending an angles of alpha and beta respectively by the point P. And now the magnetic field intensity at the point B, magnitude alone I am writing. So this is going to be equals to, let us suppose it is carrying the current I and from down to top, let it be. Then what is the magnitude? That is given by mu naught I by 4 pi A times of sine alpha plus sine beta. And from this expression we can make two important conclusions. One is that, conclusion number 1. Let us suppose I would like to find out the magnetic field intensity due to infinitely long conductor. Infinitely long conductor. So what is the meaning of infinitely long conductor? Let us suppose if I write one conductor like this. So there is a one lengthy conductor whose ends cannot be shown on this diagram. Then this kind of conductor will be called as an infinitely long conductor, and which is carrying the current I, and let us suppose here is a point B and which is at a perpendicular distance of A as I have written there. And now what is the magnetic field intensity at this point B? So for this finitely long conductor, I have angles alpha and beta which are subtending at adherents. And for this case, the same alpha and beta are going to be equals to 90 degrees because it's infinitely long, and the point P will subtend an angle of 90 degrees and 90 degrees on either sides. Then by substituting this information back to this expression, we will get the magnetic field intensity magnitude as a mu naught I divided by 2 pi A. This is the magnetic field intensity due to infinitely long conductor. Now let us rewrite the, I told you here we have the two important implications. One is that infinitely long conductor and another one is semi-infinitely long conductor. Semi-infinitely long. What is the meaning of this semi-infinitely long? So it is nothing but basically infinitely long conductor only. But the point P, which is at a perpendicular distance of A, lies near to one of the end. Here, somewhere on its length, the point P is lying perpendicularly from the conductor. Whereas here, the point P is lying at nearby the one of the end. Nearby one of the end. The other end is continuing like this. And now for this case, what is going to be the alpha? Alpha is going to be 0 degrees and beta is going to be equals to 90 degrees. By substituting this information back to our Biot-Savert law, and we will get the magnetic field intensity magnitude as a mu naught I divided by 4 pi a. Because sin beta equals to 1 and sin alpha is going to become 0. Therefore, we will get magnitude of magnetic field intensity as a mu naught I by 4 pi a due to semi-infinitely long conductor. Done. And this is what about the straight conductors. Now let us